A data is a measurement and observation. Anything you can imagine can be a data. Anything you can encode on a computer, anything that you can write down, you can say something about, you can measure, can be a data. Okay, we're in a data-driven world. Data has become a very valuable commodity, right? It's more valuable than gold, right? Most of the big digital companies are rich because they have data. Okay, Facebook is a company based on the data it has. Its more valuable asset is the data it has about you guys. All right. So data is a measurement, a set of measurements and observations. The data can be numerical, it can be text, it can also be images. You have to remember that the data that we have is not necessarily complete or accurate. Okay. So the Wisconsin breast cancer data set may have errors in it. It may be incomplete, such as at a certain year, the doctor may have additional techniques, additional diagnostic tests available to him, and then he may include the results for those diagnostic tests, whereas for the previous samples, you do not have that data. Okay. All right, and you also need to remember that these measurements are made only a subsample of the entire population. So we don't have the information for all breast cancer samples. We only have a selection of samples that the doctor has investigated. Maybe that those samples reflect the city that these patients live in. Who knows, right? So you have to keep that in mind when you're looking at the data set. You will see some terms used to describe data sets. A data set is a collection of samples. A sample can also be termed as an input, as a vector, and sometimes as an input vector. When I show you data, I will typically show samples on rows and variables as columns. Okay. A variable, these columns are also called attributes, features, and variables of your data. Okay. So each sample is a row, each variable is a column in this matrix. So a feature is typically a numerical value, but it's not necessarily that way. You can transform your raw data, which may not be numerical, into a different form. Okay. What makes good features is sometimes more art than science. For example, if you look at these images, where you visually see a letter, right? This is the letter D, this is the letter O. But if your task at hand is to take an image and decide which letter it is automatically on your computer. So if you are working on a machine learning method to decide what character the user has written, you would have to decide, how do you represent this data? How do you represent this image? Okay. In the most basic form, you can represent pixel intensities. So I can take this matrix, which is say an 8x8 matrix containing ones and zeros. So which pixel is on, which pixel is off. When the person wrote down that letter, which points on that grid did their pencil go through? Okay. So those are my pixel intensities. I can utilize them. Pixel intensities is sort of the raw data in this example. But is it a good feature? Will it help my machine learning method the most? Will it make its job easier? Will it make it so that my machine learning method gives me more accurate results? Okay. Another way to represent this data is to take this image and extract some information from it. Okay. So this extraction is sort of, you have to decide on a manually decide, but automatically encode. Meaning you're going to decide what features you're going to extract, write a program to extract those features, okay? But that decision is sort of manual, all right? For example, we can decide to extract the types and number of curves. So I could go through this image, each of these images, and extract how many straight lines I have, how many straight horizontal lines and vertical lines I have, and how many curves I have, okay? So this letter D, I'm gonna have one vertical line and one curve, all right? So I'm re-representing each sample. This letter O, I have no other I have no straight lines and I have one curve, okay? Once I have re-represented the data in this manner, I can then take this summary representation and apply a machine learning method on this summary representation, okay? I've of course lost some information, right? So a letter P and a letter D will have the same representation, okay? They both have a straight vertical line and they both have curves. So when you're extracting features, you have to sort of consider the nature of the data and whether you are losing information or whether the information you are extracting is sufficient for the problem at hand, okay? All right, so that's what I described. The feature extraction summarizes and captures relevant aspects of the data for your problem, okay? In most cases, the features that you extract cannot recreate the original data from the features that you extracted. So I cannot go back from the line, how many lines and how many curves I have, and recover my original data, okay? Or in the feature feature projection, in dimension reduction methods, when you go from a high dimensional data set to a two-dimensional representation, that two-dimensional representation is not going to be enough to recover your original data set. So you've lost a lot of information, okay? Your hope is that you've kept all the information necessary for your problem at hand, but you will not be able to recover your original data from it, okay? Which, if it is not relevant, you don't really care about it, right? Okay. As I said, most of the time we will generate numerical vectors. Other data types include time series, which are numbers as well, but the length of time is variable, right? So we cannot really represent it in a strictly n-dimensional space. What do I mean by that? Say we look at patient data across different visits to the clinic. One patient came to the clinic 3 times, and we collected their blood measurements, say blood glucose levels over the 3 visits. And then we have another patient that came to the clinic 5 times. And this first patient came every other day. This next patient came once a month. So there's really no easy way to align these two feature spaces. So the 3 attributes that you have for the first patient, their measurement in the first visit, their measurement in the second visit and the third visit. So that's three numbers. This one has 5 numbers, right? So just by the difference of the number of attributes you have, you cannot align them, all right? And even if you did, the first measurement that you have here and the first measurement that you have for the second patient is not really comparable, right? They may be at different stage of their disease. So comparing their glucose level at their first visit is not really relevant for the problem at hand. Okay, so you have to consider these when you are taking the data and inputting it into the machine learning method. You have to make sure that the features that you utilize are comparable across different samples. For time series, one strategy is to, rather than looking at the individual values, we can say extract the trend of the values, right? So I can extract a trend that summarizes whether their glucose levels went up or down, or by how much it went up, how much it went down over the entire course of their visits, okay? So for 3 visits, I can generate a single number representing the slope of their glucose levels. For another patient that came to the clinic 5 times, I can again extract a single number, which is going to be the slope of their glucose levels, indicating whether their glucose levels went up over time or went down over time. And now these two values are more comparable both semantically and also numerically. Another type of data that we encounter is graph data. A graph is composed of nodes and their connections. So these could be proteins, and the connections would be whether or not they interact. Okay? We can have a directed or undirected graph. A directed graph is where you have a source and a target relationship. For example, if you have a transcription factor that regulates the expression levels of genes, you have sort of a directionality in that interaction. Your transcription factor affecting, there's an arrow, the expression levels of the genes. And the graph is going to include more than 2 nodes, of course. You may have complex relationships across different nodes. Okay. Your Facebook friend network is also a graph. So there's you at the center of the world, of everything, right? And there are your friends, there are friends of your friends, there are your friends of friends, and some of these friends are connected to the other friends. Okay, so this entire thing is also a graph. For graphs, we can, again, extract summary information because they are one graph and another graph is very difficult to compare. We have to extract some summary information, such as how dense it is. So we get a single number from an entire graph, just like we took a series of visits for a patient and extract a single number. Now we can take an entire graph and create a summary information. How dense is the graph? Or how connected is the graph? How wide is the graph? How many edges do I have to go through to go from any node to any other node? What's the diameter of the graph? So these different techniques to take an entire graph and generate a single number is sort of a feature extraction step that we can utilize to summarize graphs so that we can compare them more easily in a machine learning context. Okay. Another type of data is text. I should really say text, and bag of methods is a method that we would use for text. Okay. So if I write an essay and you guys, each of you write an essay, or if I write 10 essays and each of you write 10 essays, can we develop a machine learning method that can predict whether, given a new essay, whether I wrote it or you wrote it? Okay. Or if we say put all of our essays together, present it to the machine learning method, and say here's the essay, here's who wrote it, and then later on we will provide a new sample and ask the machine learning method, tell us who wrote this essay. Okay. The machine learning method, before we can present the data to the machine learning method, we have to take the essays and convert it into a numerical form. Okay. For most machine learning methods, we would have to do that. One strategy is to use a bag of words approach. So rather than providing the entire essay as a raw data, we will first pre-process it and get frequency of words from that text, from that essay. So I use the word A 20 times, or let's say with a frequency of 0.1, and I use the word apple at a frequency of 20% of the time in my essays. Okay, so my essays are very simple. All right, so now we have a list of words and their frequencies. My essay and your essay are more comparable now. They have the same number of features, and the features align well with each other. I'm counting the number of times I used A and the counting number of times that you guys used A. Okay, so each attribute is consistent across different samples. All right, so that's one approach that we can use to pre-process text, extract features from it, so that we can later utilize a machine learning technique. Sequences are like texts, except rather than having a natural language where they are composed of words, now we have a sequence of letters that are not really natural. It's not a natural language. Let's just give an example of gene sequences or protein sequences, which are composed of a series of letters, right? It's a long series of letters. There's no really one word and the next word, right? So how do you represent this in a numerical context? And we'll see some strategies to take this sequence and convert it to a numerical form, okay? Three-dimensional structures or images are other examples that we can take and extract features from. Again, the idea is to take your complex object, complex data, and summarize it in a way that captures relevant information for the problem that you are trying to solve. Okay. All right. The variables that we create or the variables that we have can be categorical or continuous. Categorical variables, categorical attributes can be symbolic or discrete. They can be nominal or ordinal. Nominal means they are categories, but there's no numerical scale comparing them. Okay. For example, the taste of a food is a nominal attribute. It can be sweet, salty, sour. There's really no way to rank these. Okay. So sweet and salty and sour, you cannot put them in a particular order, right? There are three different things. To represent the taste numerically, if you say, okay, I have the taste attribute, here's one food item, chili peppers, it is hot. We'll say hot is 4. And then I have another food item, cinnamon rolls is sweet. We'll give it a score. We'll give us a sweet. We'll say sweet is 1, salty is 2, sour is 3, and hot is 4. Okay. So taking a nominal attribute and artificially giving them numbers is not the correct thing to do. So this artificially enforces an ordering on your values, and you're going to confuse your machine learning method. In a way, you're gonna make your machine learning method think that sour, there's a relationship between sour and salty that's ordered. Okay. The correct way to represent this data would be to create 4 or 5 or however many different tastes you have. So taste is sweet. So the sweetness will be one attribute. Saltiness will be another attribute. And sourness will be another attribute. And being hot is going to be another attribute as well. When you have one food item that's, say, chili peppers, you're going to say it is not sweet, it is not salty, it's not sour, it is hot. Okay. So this is sort of a binary encoding for a single attribute. A cinnamon roll is sweet, not salty, not sour, not hot. Some of the machine learning libraries will handle this for you, but some won't. So you have to check the capabilities of the machine learning library. Library in the sense of the function that you utilize in MATLAB or Python. Are they already handling categorical data? If so, you can provide your data and say, by the way, this is a categorical data. Okay, then that method will handle it for you. If they don't support it, then you would have to take the data, transform it yourself before you give it to the machine learning method. Okay. All right. Ordinal values can be ordered, such as colors. How green a color is a scale. You can give different values to it. or words like small, medium, large, you can assign a number to them. Okay, so you don't need to separate into 3 different columns. You can just say size, small is 0, medium is 1, large is 2. Okay. All right. Categorical values are typically assigned as integer values. Continuous variables will have real values. So floating point attributes will be continuous. Okay. All right, so for most problems, the variables will be numeric and continuous, but they don't have to be. When they are categorical, you have to inspect and see if they can be ordered. If they can be ordered, you can assign a particular numerical scale. If they cannot be, then you have to split it up into multiple columns and represent it that way. The numerical values can be binary, 0 or 1, -1 or +1. 1 or 2, so depending on the problem, you may see different values for binary values. They can be scalar types, such as integer and real. You can have complex numbers. A complex number can actually be represented as 2 real numbers, right? You can split the real part and the imaginary part and say, my old attribute was a single complex value. I've transformed it so that it's 2 columns now. First column representing the real number and the second column representing the imaginary number. Okay. A vector valued variable is something that is composed of more than 1 attribute. Okay. Again, you can think about it as multiple columns within your data. Color values in red, green, blue scale is one example where rather than have a single number representing the color, you now have 3 numbers representing how red, how green, and how blue it is. Okay. All right, so that's our data. Let's now go through some statistics terminology and how they apply to machine learning that we're going to cover in the course. Okay. All right. So when we look at the data set, we have to remember that it's a sample of the entire population. And that is because of the practical reasons we don't really have the luxury to have all the data. And if we had, we wouldn't have to go through the trouble of applying a machine learning method in the first place. After we collect the data, we can analyze it in 2 different ways, using a descriptive statistics or inferential statistics. A descriptive statistic is things like taking the average, looking at the standard deviation of the data. So you sort of summarize the data and gets different characteristics of the data. Okay. Inferential statistics is sort of more complex discovery, data mining, machine learning methods fall into this category. Okay. So we try to discover patterns in the data, and we try to make inferences about the entire population or inferences about some unseen samples that may be presented to the machine learning method. Okay. All right. So examples of inferential statistics are hypothesis testing, estimation, forecasting, so making predictions, finding correlations between variables, regression analysis, where you would take some of the variables and try to predict another variable from them. And some of the other statistical questions that you ask are also part of inferential statistics. Okay. We can apply univariate or multivariate statistics. Univariate refers to having a single variable. Right? So if I just have the height of a person and no other information, that's a univariate sample. I only have 1 variable, 1 column in my data set. And these are typically easier to look at, right? For a univariate, you can look at the mean and variance among other things. A multivariate data set is where is the thing that we're gonna encounter the most in real life applications. You can summarize each variable separately, which means you can find the average and the variance of each attribute separately. You can also look at the relationship between pairs of variables or relationship between all attributes, all variables. So we have a measure of covariance, which tells us how one variable changes with another variable. Okay. Correlation is also a multivariate measure that we can use to summarize relationship between different variables. So these are, when I have different columns, how do I characterize them? How do I summarize them? How do I sort of get a sense of what they are and put a number to it, essentially. Okay. All right. So these are the types of statistics that I can do. The types of analysis that I can do are exploratory and confirmatory. Okay. An exploratory analysis is where I try to recognize a non-random pattern or structure in the data. Okay. So data mining, where I'm given the data and I try to discover patterns from it, is an exploratory analysis. For example, if I'm sort of the Amazon website and I try to discover patterns between buying, between your purchases, here are other customers that after purchasing this, purchase these other items as well. So that information is extracted using a data mining approach. Okay, so they have a large collection of data and they go through it. They find patterns that are recurrent, and they make use of it when they make recommendations. Okay. A confirmatory analysis is after you have a well-defined hypothesis in mind, you can ask a statistical question and pick a statistical hypothesis test that you can apply, such as a t-test or a non-parametric test, and then answer the question of whether your hypothesis is correct or not. Okay, whether the data supports your hypothesis or not. Okay. For this week's assignment, I'm going to have you guys work on some basic statistics. We're going to look at the data set and find relationship between columns, find the correlation, find the p-value, and also plot it. So I just want to make sure that you guys are able to do that with a sample data set before we move on to machine learning methods in the later weeks. All right. Okay. Let's take a short break and then I'll continue with an overview of machine learning methods and the types of machine learning methods.